In this video, we're going to look at the revision questions on curved mirrors. Now, what we have here is Moana, who's studying different types of mirrors for a school production. And for the first part of the question, you're required to draw a label diagram to explain the law of reflection, which basically states that the angle of incidence is equal to the angle of reflection. Now, on this diagram, what I'm going to do here is I'm going to draw the guiding lines first, and you should use a ruler to do this. And let's label the plane mirror surface and the normal, which is 90 degrees to the surface. Let's include the incident ray from left to right. And of course, this is the reflected ray. Now, the angle of incidence is measured from the normal. So please remember that. And of course, the angle of reflection is measured there as well. Now, as you can see, this matches the statement. Angle of incidence is equal to angle of reflection. And for part B, Moana is looking at a vertical plane mirror. So draw a ray diagram to show that Moana needs only a mirror that is half her height for her to see a full image of herself. Now, we've already drawn the image or Moana's image on the right hand side of the vertical line. So what I'm going to do first is I'm going to include guiding lines. I'm going to draw first from her eyes to the top of her image. Now, basically what a mirror does is it's a kind of illusion. It's kind of deflect or reflect a light ray and make it seem like it's coming from behind the mirror. And I'll do the same thing from her eye to her feet, and there'll be a guiding line from the mirror to her feet and to the top of her head as well. And before I include the light rays into the ray diagram, what you have to understand is there is no light ray that can travel behind the mirror. So this is the virtual side, and where the light ray travels on the left hand side, that's the real side. Okay, to complete the diagram, so there is a light ray, don't forget the arrows, coming from the top of her head and bouncing off the mirror or reflecting off the mirror towards her eyes, and of course from her feet and towards her eyes. Now, the lines behind the mirror, because this is a reflection, so you make it seem like the reflected ray towards her eyes seems to be coming from behind the mirror. So since there is no actual ray behind the mirror, so we'll call that the virtual rays, and it has to be drawn with dash or dotted lines. Make sure you remember this. And now if you look at the real rays on the left hand side, you will notice that the reflection on the plane mirror follows the law of reflection, which is angle of incidence is equal to angle of reflection. And now from the diagram, we can prove that from the two extreme ends where the reflections are to see the top of her image and the bottom of her image, anywhere in between forms the mirror or reflective side that is required to see her full image, which is half of her height based on geometry. Okay, let's move on to the next part. Moana then tries to design a spotlight for his school production. Now, there are different types of spotlight. So in this case, it depends on what we're trying to do. Okay, we may want to try to focus the light onto a point. We may try to focus the light into a wider part of the stage. But in this case, it's trying to create a lamp which will reflect the light in the horizontal direction. Basically, as shown in the diagram, the reflected rays are parallel to each other along the principal axis. Part C, state the type of mirror shown, so that's obviously a concave mirror. Part D, state the name of the position F where she has placed the lamp. Now, the fact that the reflected ray is parallel to the principal axis, it means that the lamp must be positioned at the focal point of the concave mirror. And for part E, explain why the lamp has to be placed at the focal point F to function as a spotlight. So basically what we're trying to do here is we're trying to make every reflected light to move parallel to the principal axis, falling evenly onto an object onto the stage, which is quite a distance away from the concave mirror. Okay, let's move on. She then places the lamp further from the mirror and notices that the light ray from the lamp reflects straight back to the lamp as shown in the diagram. So state the name of the new position C where she has placed the lamp. Now this is known as the center of curvature, and this is basically the center of a circle or a sphere, because the curved surface of the concave mirror is actually part of a spherical surface. Explain why the light ray reflects back as shown. So basically what's happening is that the light ray from the lamp, when it hits the curved surface, it is along the line of the normal, and that's the reason why there's no angle of the angle of incidence is 0, and therefore the angle of reflection is also 0. She then positions the lamp somewhere between C and F. C is the center of curvature and F is the focal point, and you're required to draw a ray diagram to show the position of the image. So let's include the notation for a concave mirror, and this will be the real side and this will be the virtual side. And now let's include our lamp to our diagram. Now you notice that I've positioned the lamp with the base along the principal axis. Now when we draw a ray diagram, we don't have to draw the actual object. So what we just need to denote the lamp is with an upright arrow with the base on the principal axis. And since this is a concave mirror, so the light ray coming from the top of the object, which is parallel to the principal axis, will be reflected through the focal point as shown. Let's not forget the arrows. And the light ray that is reflected off the pole of the mirror will be reflected off at the same angle according to the law of reflection. And where the two reflected light rays meet, that's the position of the top of the image. And in this case, you can see that the lamp is actually inverted, magnified, and real because it is formed by real rays that intersect each other. Okay, the next part, the focal length of the concave mirror is given as 25 centimeters, and the length or the object was placed 30 centimeters away from the concave mirror. And in this next few parts of the question, you're required to calculate the position of the image. Now, we've drawn the ray diagram earlier on, but what a ray diagram does is it is only able to estimate or predict what the image is going to be like. So even if you draw to scale, it's not accurate, it's just an estimation. So now what we're going to do here is we're going to use the mirror equation, which is actually the formula given to you here, which is 1 over f is equals to 1 over do plus 1 over di, where f is the focal length of the mirror, do is the distance of the object from the mirror, and di is the eventual distance of the image from the mirror. And we're going to use the mirror equation to calculate the position of the image. So we know that f is equals to 25 centimeters. Now you should add the plus sign because the notation here is, or the convention here is that for a mirror, anything on the left hand side or on the real side will be positive, and anything on the virtual side will be negative. Now do take note that sometimes during your NCEA exams, they like to flip where the real side is on the right hand side while the virtual is on the left hand side. Okay, so in this case it's given that the object distance is plus 30 centimeters because it's on the real side obviously. And if we include the numbers into the formula or the equation, so 1 over plus 25 is equals to 1 over plus 30 plus 1 over di, and we need to rearrange the equation. So if you do it right, you should get di, or the distance of the image from the mirror, will be 150 centimeters. Now let's deduce the magnification factor, because we can see from the ray diagram the image is larger than the object by a certain amount, but the ray diagram is just an estimation. So using the formula, m is equals to, in this case, di over do. So m is equals to 150 over 30, and which is equals to 5. This means that if we had drawn the ray diagram to scale, the image should be about 5 times the size of the, or the height of the object. Next, Moana now moves the lamp closer to the mirror as shown in the diagram. She sees a clear image of the lamp on the wall. Now this is the position of the image. So the height of the image is twice that of the height of the lamp. The focal length of the mirror remains at 25 centimeters. Use the equation again to calculate the distance from the mirror to the lamp for this situation. Right, based on the information given, we know that the height of the image is twice that of h naught. So if we rearrange that, hi over h naught, the fraction will give us 2. Therefore, according to the magnification equation, di over do will also be 2. So this means that di is twice that of do, which means that the distance of the image from the mirror is twice that of the distance of the object from the mirror. So we can now use the mirror equation. So 1 over plus 25 is equal to 1 over do. So do is unknown, plus 1 over 2 do, which, because we know that the image is twice that of the object distance. And if we rearrange this correctly, and you should get do to be equal to 37.5 centimeters, which means that di is twice of that at 75 centimeters. Now, I will always recommend a student to sketch a ray diagram to verify the answer, just to make sure that they've put the correct sign when using the mirror equation. Moving on, Moana observed that it is possible to get a virtual image of an object using either a concave or convex mirror. So explain the difference between real and virtual images. Now, for real images, they are basically formed by real light rays meeting at a particular point, forming the image. Right, so this is, you could say that the light rays are actually converging into a point, and because of this, the real rays can form a real image and can be therefore captured onto a screen. However, for virtual image, because they are actually formed by virtual rays meeting together, therefore, since the light rays are not real, they cannot be captured onto a screen like a real image. For part O, on each of the diagrams below, use a ruler to draw the path of 2 rays of light from an object to produce virtual images for both concave as well as convex mirror. The vertical line represents the curved mirror. Now, you got to make sure that you practice this, because you actually have to know the position of the object to produce virtual images. So let's do the concave mirror first. Let's start by drawing the curve to indicate the concave mirror along the vertical line. And of course, you should know that the left hand side is the real side, while the right side is the virtual side of the mirror. And you have to memorize that to get a virtual image for a concave mirror, you have to position the object between the pole or between the mirror and the focal point, as shown. And from the top of the object, the light ray that is parallel to the principal axis is going to be reflected through the focal point. Don't forget the arrow. And the light ray that is reflected off the pole is going to be reflected off at the same angle according to the law of reflection. So it's going to be about that. And you can already see that the two reflected rays are not going to converge on the real side, but it's actually coming from a point on the virtual side. So let's draw the virtual rays, and this is the position of the image. And from this diagram, we can conclude that the image is going to be upright, enlarged, and virtual. And let's do the same thing for the convex mirror. Now we'll draw the curve for the convex mirror. And you should know that for a convex mirror, the focal point is on the virtual side. And of course, the left-hand side is the real side. Now, this is a easier diagram to draw as compared to the concave mirror, because the object needs to be on the real side anyway. And it's going to produce a virtual image at any position that you choose. So let's indicate our object with the letter O. Let's draw our ray diagram. So the first light ray is going to be parallel to the principal axis, but this time around, because this is a convex mirror, the light ray is going to be reflected away from the focal point, which is behind. So I've drawn the guiding line here. So the light ray is going to be reflected off in this direction. Okay, let's not forget the arrows. And we can remove the guiding light and replace it with dashed lines towards the focal point to indicate that this is the virtual ray. And now let's include the light ray towards the pole, which will be reflected off in this direction. And we can include our dashed line for the virtual ray. And this will be our position of the virtual image on the virtual side. And we can describe the image to be upright, smaller, and virtual. Now, you should notice by now that for both diagrams, when we have a virtual image, it is always upright. And for the last part of the question, Moana places the lamp 15 centimeters away from the convex mirror with a focal length of 20 centimeters. Use the mirror equation to calculate the position of the image. So we have the mirror equation here, 1 over f equals to 1 over dO plus 1 over di. Now, do take note that for a convex mirror, the focal length is on the virtual side. So you have to remember that you have to put a negative sign, so it'll be 1 over minus 20. Now the object is always going to be on the real side, so that's going to be 1 over plus 15. And you're going to plus 1 over di, and if you rearrange that correctly, you should get di to be minus 8.57 centimeters. The negative sign basically indicates that the image is going to be on the virtual side of the mirror. As mentioned earlier on, a potential problem is when students are not sure whether to put a positive sign or negative sign when using the mirror equation. So it's always a good idea to verify your calculation using a sketch of the ray diagram. Let's do that now. This is our convex mirror, this is our virtual side, and this is our real side. Let's put the object. Now we know that the focal length is 20 centimeters. So therefore, DO, which is 15 centimeters, is going to be somewhere around here. So let's put our object. So indicate with the letter O. Let's draw our light rays. So the light ray that's going to be parallel to the principal axis is going to be reflected in this direction. And the light ray that is reflected off the pole is going to be reflected off in this direction approximately. Okay, so from this diagram, you can verify that your image is going to be smaller or between the pole and the focal point. So in this case, 8.57 does seem very reasonable. Okay, so this will help you to ensure that you are on the right track. Okay, so this ends our revision on curved mirrors, and hopefully that has been helpful.